Thanks for having me here as a non-fracture person and knowing very little about breakup even on the river ice. I think Steve Daly gave a very good overview or introduction that hopefully will help the communication on my talk too. I actually was going to show these videos, but this first one was already shown by Steve. The good thing about the YouTube. The second one is another type of breakup if we talk about it. And this one is a little long. I'm not going to show it, but it's a very interesting one. And if you're interested about breakup in a smaller, steeper rivers, you may want to take a look at that. But this one is I will just show part of that sound is helicopter sound, so I turn it off. This shows ice coming from upstream, pushing into a reservoir ice cover. So here we don't see any bank effect. If in a river you will have bank friction, but this one it doesn't. But shows another type of breakup. Upstream you will see the river there. Okay, that's what I want to show. And I want to show this before I start my PowerPoint as a background. And here I want to show an old simulation of river ice formation on actually ice jam formation on the Niagara River. What we have, and I will show that again. This is Lake Erie, and this is ice boom. And the purpose is try to control the amount or the rate of ice discharge coming into the river. When you have too much ice going into the river, you can easily jam this. Form ice jams here at the NIPA hydropower intake. This is Niagara 4 here. So I will run this in loops so we can see how the numerical simulation or mathematical model develops and initiates the ice jam and develops it. Okay, just repeating this. Okay.
Why is it getting stuck there?
Why it's stuck there?
Yeah.
We'll talk about that. Okay. Yeah. Actually, used to be one of the key questions for river ice people working on ice jams is where it's stuck and at what time. Okay, so if we have the model, we have to do validation. We have to be able to the simulation should be able to reproduce the time and location of the jam, let's call it. Okay. So if we talk about river ice model, we try to include everything as much as we can. So we are talking about all of these: energy budget, heat exchanges, and hydraulics, because everything is related to the flow. and water temperature and thermal ice transport, freeze up, and all these. But today I will mainly talk about the dynamic transport of the surface ice and jamming. And what we don't know actually more on the ice cover breakup. Okay. And why do model? Well, we try to model the coupled ice and flow process together. But for river ice people, as Steve already mentioned, at the beginning, at least to me, ice jam related flooding is of the interest to most of the people. So there were a lot of ice jam studies, and then for hydropower operations, especially in large rivers, how you manage the ice on the river can make big difference on the power production. And then if you go further on that, then you can of course consider what's the effect of ice on the channel morphology, sediment transport, bank stability, and of course you can talk about ecology and all these things. That's from the application side, but I feel more importantly, that's where you get support, of course. More importantly is the model. When you link everything together, put them together, then you will see where are the gaps of our knowledge which deserves more study. Okay. Now here I just want to show a few examples. This one is the animation I just showed. The Niagara River, the lake is here. The jam usually happens at the intake, partly because of the suction of the flow and converges, makes the ice converges. And that's the upstream end of it. The ice boom tries to control how much ice can pass this boom into the river. And it looks like this on the design chart. And this is where the hydropower intake is, and the jam initiates from here, but at this point it's not quite jammed yet. The ice is still moving, but eventually it jammed across and then it's backed up and cause some flooding, of course. So that's really just the dynamics. And more recently, we looked at the freeze up. And this is a banded ridge on the Yellow River. And this is just shows a time series or time sequence of the ice cover formation. As we said, that ice cover on the river in the main channel is always start from ice jam or jamming of the ice. And this just shows that's the beginning, the first jam formed here. And when this jam develops, it backs up the water and slows down upstream, and then we have another cover formed with open water in between. And you can see the comparison of this with the satellite image. And we also, since the river ice dynamics modeling, actually the idea initiated, I would say, trace back to the sea ice dynamics. So now we have this, we say let's also try on this Bohai Sea. Actually, it is a bay with tidal effect at the inlet of the bay. And when we do the simulation, we compare the model result with the observation. Okay. And the interesting thing is, on this tidal basin, let's call it, the ice cover thickness is actually banded. It's not continuous. And that is mainly because of the back and forth of the tidal action. And the model needs to be able to show that, and that's what we have here. So these are just few examples of the ice dynamic modeling. Let me now go into an overview. I think, as we said, almost 90% of the ice in the river start from frazil, and then flocculate. Some go to the anchor ice, and most of it come to the surface and start to move downstream. During the freeze up, when they're moving to downstream, at the same time you get more and more ice produced, so the concentration gets higher and higher. Somewhere it will jam, and that is starting off the main ice cover, or ice cover in the mainstream of the main channel. So actually the ice cover formation is just a case, special case if you call it, of ice jams. Okay. And if we want to include all these processes, we need to be able to get the water temperature, surface concentration, suspended ice concentration, frazil, and the thickness variation, and all these things. And we try to do that. This is a small stream, but it's a picture showing different types of ice you can have. This is the border ice. Well, this is in a band, and typically it's deeper here, shallower here, slower velocity, higher velocity. So here you form smooth border ice, okay? And here you have ice pans, pancake ice start to develop, and you can see them. And then the border ice on this side, I call it dynamic growth of the border ice. It's due to the interaction of the surface ice flows with the bank. And ice can form in different forms. As we see in a very slow flow area, almost quiescent, this is the kind of ice you will see. Okay, we call it skim ice in river people. Not quite the same as grease ice, but anyway, it's very thin sheet of ice floating on the water surface. And then you into a mainstream or higher velocity, they begin to cluster, or could be even bigger and bigger if you are in a rapid. And actually in the rapid you see ice balls this big from frazil ice. Few pictures. Ice flow on the Peace River in Canada, on Yellow River, on Elk River, and that's also on Yellow River. Okay, showing this, just maybe there will be some suggestions, ideas coming from the group here. So we talk about surface ice transport. Here I only want to talk about mainly the dynamics, assuming all the thermal effect is coming into the mass of the surface ice. So we need large ice discharge. Just like traffic jam, you need a lot of traffic or a lot of cars. The jamming condition, in the early days, people talking about when you have bend, you are going to get jam. When you have slope change, you are going to get jam, and all these things. But all these phenomena can be expressed by the convergence of the ice motion. When it converges, then you are going to get jamming quickly. And of course, this related to all these hydrodynamics and channel geometry and so on and so forth. Freeze-up jam and breakup jam, mechanically they are the same thing, okay, except the effect of the thermal. One is freezing, one is melting. And once you get a freeze-up jam, it stays there over the winter, and breakup jam, of course, will release, so it's a shorter term. And the river ice people most of the time are thinking about the problem with the breakup jam, but with the lack of ability, that put it more straightforward, on fracture and all these things, the breakup side we know very little. Okay, few examples of the jamming. This is just happened, like same as breakup. It's very hard to know where and when the breakup happens. And for freeze-up, we know when we will have freeze-up, but when and where we get jam, it's hard to catch. Okay, this just happened. I got this. This is a Susitna in Alaska, and this shows the beginning or the formation of the ice jam. Okay, flow upstream, downstream, and give you some idea of the jamming mechanism. This is another one, and on Peace River, we see similar thing. This is upstream, this is downstream. And this is about the point where the jam is going to initiate. So once its jam initiate, then any more ice coming from upstream will accumulate behind it, and then eventually form ice cover. But before this, of course, we have border ice. So when this ice pushing in from upstream, we are going to also have the ridging, shear line ridging here. Okay. A few more pictures just give you a feeling of what we see in the field. Like this. Now this one, these are all on the Yellow River. You see a lot of sediment there too. Okay. And this is after the ice is released, and we can see actually under the ice cover near the border, we actually have frazil accumulation also on the underside of the ice cover. Here's another one, again on the Yellow River. This is what we typically see. Okay, and that's a smooth ice cover with cracks. But this is, I have never seen something like this before. You can see the ice cover, actually, look at it, you have cracks in a rectangular, almost rectangular pattern. Very regular. And I have not seen this in other rivers in US, Canada, or Europe. Okay, so I say, why is that? Well, then I found something, people call it the ice wedge crack. This is a picture from the paper by McKay in '74. This is the pattern you will see on ground surface. Okay, and this is the explanation I took out from the book by Wu. Okay, so two things. Why then it happened on the Yellow River, that part we haven't seen in other places? Maybe because there was no snow cover. It's a very dry area. Okay. What's the effect of this on breakup? I don't know. Maybe I get some input from you. On a nice ice cover, if we cut the section through the depths, this is what we see. So in a way, this is the initial cover. It's managed on from the St. Lawrence, so it's managed to get a smooth ice cover. And on top of it, we have snow. Below it, we have the frazil accumulation from the initial period. Then after that, this is due to the thermal growth. Now, to model it, I just want to show the hydrodynamic equation. It's a two-dimensional hydrodynamic equation. Everyone working on the river ice or rivers know that we need roughness of the flow or flow resistance. And when we starting on modeling the ice dynamics, we say, well, we think the ice roughness is proportional to the thickness. At that time, I just said, this is how I feel. But why is that? Okay. Recently, we looked into this, and actually, we can show that why the roughness or flow resistance increases with the thickness of the jam or accumulation is mainly due to the head loss due to the seepage flow in the jam. And actually, you can calculate that. Okay. So, surface ice dynamics really no different whether you are in lake, in sea, ocean, or river. The difference is river, we have a much smaller time scale and spatial scale, and we have boundary effect. And at the time, when we were starting working on this, I was looking for a good method or suitable method to do the ice dynamics. And we looked in different methods at the time, and we decided to use SPH method. I don't particularly like the term of SPH. It's a mathematical term. So physically, I think we can call it discrete parcel. Parcels of mass we are looking at. Okay. And then I say I like this because it's easy to see what's going on. It's a Lagrangian type of approach. And then we compared with different methods people have used in the past in sea ice and things like that. Found there are actually problems in the traditional finite difference method and those used. But anyway, let's continue on this. I think if we do the formulation, the momentum equation, everybody knows that, and this is in the Lagrangian form. Okay. And then we have all the forces, internal resistance of ice, wind, water drag, gravity component, because the river surface has a slope. In rivers, we don't need to worry about Coriolis, but you could include it, we don't. Then, of course, we need other equations, so we have same number of unknowns and equations. And we need to have the boundary effect from the river bank, the friction. Now, the constitutive law at the beginning, whether it's in lake ice or in sea ice, we all use this viscous plastic model. the main thing we see the difficulty or problem is this P star term. If we use this P star as the way Hibbler used, then it's a constant everywhere. Doesn't matter how thick your ice accumulation is. And Wagen and Rumor, they improved it into something like this. So now you see this P star, and it's another term proportional to the thickness of ice. And I still remember at the time, Rumor told me they had hard time to match with the data without this term. Okay. So now going to the river ice. Well, before we do the dynamics, there are a lot of studies on ice jams, on the static ice jams, to calculate the thickness profile. And this is the way we formulate it. Okay, this is the internal friction angle of the ice accumulation. So we used this, and this whole thing is actually, if you let the dynamic equation or condition goes to static, then you will recover the static ice jam profile. And we add this here. It's plus and minus is convergence and divergence. It seems to be trivial. If you have ice divergence, then the stress should drop. And if you don't consider that, then you're not going to have good simulation for ice jam release. Okay. In laboratory, just to see what an ice jam may look like, it's like this. Okay, and this is not a good picture, but if you look carefully, you will see the seepage flow coming out. Okay, we just artificially create this jam by blocking it with a wire mesh. And we have to remember this. In rivers, the scale may not be the same. Okay. So, talk about validation. Besides being able to determine when and where the jam will initiate, how do we know our profile is right? Before we have any field data, what we did was we checked the water level along the channel. There's record on that, and see if it matches. But that's an indirect check. Then we have this data from Belthouse on the Thames River. And nobody wants to get onto any ice jam when it's not freezing or not frozen. And this one is a midwinter jam or midwinter breakup jam. So this is a set of data that we compared with the model. Okay, and just want to say that we have to remember that the scale, the vertical scale and the horizontal scale is very much distorted here. So the actual jam should not be looked at like this. It's stretched out horizontally. I say this because some hydraulic engineers keep telling me there's a downward jet at the toe of the jam. It doesn't. Okay. Now, when a jam formed or cover formed during the freeze-up, if the flow condition or upstream flow condition changes, you may have a surge of flood coming down. The formed jam could collapse, and we call it a secondary consolidation. And then the thing is, when this happens, or before this happens, there may be already jam was in the river for a period of time, and then we already formed a thin solid crust there. And this will give us extra strength. So when we look at whether we will have secondary consolidation or not, this effect needs to be considered. And this was actually mentioned by Michel in '78, and then by Dave Andrews in '99, and they both suggest some strength numbers for this. And these are just two numbers from two field cases. So how does this really, the strength changes with the ice flows mixed into the freezing layer? Maybe needs a little bit more study. And if we looked at that, if we have a freezing layer, then your jam shape may be different from without the freezing. Okay, so the solid crust could have effect. Now we go into the spring breakup, and Steve already gave a very clear overview on what's going on there, and this will just probably repeat some of it. Thermal meltout, well, the model can do that now, okay, because we consider all the thermal effect and melt the thickness of the ice cover into almost zero. A mechanical breakup is a balance of the driving force and the strength of the cover. And all of these, the current wind drag, streamwise weight of the cover means along the slope, gravity force, and the force from the ice rubble accumulation, pressure variation on the underside of the cover due to the river waves. And all these are the driving force, and the bank resistance is the force that balance it, try to. If we look at the thickness variation over the winter, you can see it's pretty much like this. This is on St. Lawrence, it's well managed, so we don't have a mechanical breakup. Anytime, if we have breakup at this time, we probably will get ice jam, most likely. If we get breakup over this period, that is thermal meltout. That means we need ice mass. Mechanical breakup, one way of looking at it is prefrontal mode in the early stage that has long sections of ice sheet broken from the bank. And the frontal mode, this is really the point of, I consider to be the mechanical breakup. Okay, and in the early years, Suliakovsky and Belthouse after that did more detailed analysis. Basically, they say the stage increase above the existing ice cover developed an empirical criteria. And this is really saying that depend on the geometry of the river, the flow condition, and the heat input, okay, and then you can determine when the breakup will happen. But this is the kind of thing that in the early days we cannot model all these things. But if we can model all of these things, then what we need is really the input from the hydrodynamics in the flow and the strength of the cover. Now the strength of the cover changes. Of course, changes with the thickness. And in the spring, you could have weakening of the cover into this kind of material. Okay, it's basically the melting between the ice crystals, so you lose the strength. Okay, and if you leave it there, it will eventually get into something like this. So besides modeling the thickness change of the ice cover, it would be useful to also model the melting, internal melting due to the shortwave radiation. And this was done in the early years by Bolotov, and Ashton refined it. Okay, and it's a very simple idea to do this actually. And this is what Ashton did. Consider the ice crystals on the plane view, cross-sectional view looks like this, and melting starting from here. And he compared with the porosity and strength with some of the field measurements on the limiting condition. Okay, and Steve already mentioned that at the very beginning, this is pre-breakup period. It's the theory is mainly based on the beams on elastic foundation, and you either detach or break from here or in the middle. And that idea is there like this with the uplift pressure, and then break from the shore. And Beaufort at the time said the E value will be this much, and Belthouse in the field he found this, of course in a later stage of the ice cover. Okay, and then after this we'll go into the far-spaced transverse crack, mainly considering the effect of the river bend. But really the real breakup comes when we have a close-spaced transverse crack. In other words, the ice cover broken into shorter pieces. So this was the idea that initiated or beginning with Suryakovsky, and the Belthouse carried out further refinement on this. And the idea is, like Steve said this morning earlier, you can get breaking at the bend, okay, due to the movement from the hydrodynamics. And Belthouse analyzed this and came up with an empirical relationship, as this picture you already saw this morning. From the modeling point of view, I'm actually not too concerned with this. I think what we really need to know is after this, okay? And again, I show this, the band, and you can see that on the Yellow River, the same picture, you do have cracks like this in the band, and this here. But at the same time, you can also see cracks like this. I just show this to you to see if you have any suggestions or points. So summarize, in the prefrontal mode, in the early stage, we have longitudinal cracks along the channel, and then we have far-spaced transverse cracks, mainly considering the band effect. Then this is more close to the real breakup and the ice run. So we are looking for close-spaced transverse cracks. Fragment into rubble, I don't think we know anything about that. Once you have that, then you have ice run, then you have jam formation and release. And this could go repeatedly along the river. including, of course, the possible thermal effect of melting of the ice and so on. So again, we are in a loop like this, okay? And this is what we really like to know better. So in a simple picture, if this is the cover, we could have ice mass or rubble coming from upstream and exert force on this leading edge up along this and underneath, bending it. But at the same time, we are talking about really the surge or flood wave coming from upstream that could cause the propagation of the breaking front along the river. And that's, we call it short space. And this is a field observation describing what they see and what happened. Okay? When a flood wave comes, there's a rapid rise of the cover, cracks spaced at 50 to 200 meters apart appears across the river. And okay, this movement was accompanied by widespread breakage of the cover with cracked lines associated with ridging and so on. And the broken ice front was moved at a speed approximately equal to the free surface surge wave, which is wave speed of the shallow water wave, square root GH, or square root G times depth of the flow, and so on. So we said, and Steve started looking at the wave ice cover interaction. So we followed that and consider this, both the mechanism already mentioned, and try to do some nonlinear analysis. Okay, I'll quickly go to, so when we combining the flow equation with the ice cover equation, elastic plate, we get a nonlinear equation like this, and then we get a solution. The wave speed indeed, the open water wave is like this, and the wave speed with cover is modified by 1/10 of the amplitude of the wave. And then we have the wavelength and wave profile. So profile looks like this, and then calculate the bending stress and so on, and get a few examples. If water depth and the E value and the thickness of the cover, and typically in the river, this is about the range of the ice cover thickness you will have. And here another one, the depth 3, you get something like this. And you can see the value is in the range of what they observed. Okay. But we have not really tried to couple this into the model, because before this I was quite confused about this ice breakup process. But I think we can actually try to do this, and let's see what we can do. Okay, this is what you see in the video, and this is the river in Poland, and you have similar thing. And the model can do this, and mainly we are talking about the compressive failure. And you can see this can progress along the channel. And here, this figure is distorted, exaggerated. This distance is actually very small. Okay, and Yesterday, I think Erlen was asking about what's the friction coefficient. Okay, let's say calibrated, and the friction coefficient we got 0.26. Beltos calculated using the static ice jam theory, he got 0.24. So that's what we have. This is just in a band you get the similar modification model. Now there's all these things, mechanism involved, and we don't know too much of fracture mechanics, and all these factors are involved, including the weather condition, water temperature, thermal effect, melting internally or externally. Well, what do you do? Well, I think we will consider river as our laboratory. Okay. The ability of monitoring what's going on is really improving. So I just want to take one example. So this is the breakup on the St. John's River. We look at this stretch of the river, and they have the data. Data means what? Nothing on the mechanic side. Data on the water level change and the timing of all these. So this is the river, or it looks like this. So we are trying to reproduce what happened in the field. Okay? Manually or artificially. So we were able to match, let's call it calibrating at this point, with all these discharge water level data along the way, and that implies we may be simulating the breakup process correctly, but that's artificial because we have to manipulate it. Okay, but after doing that, ideally we then can go back, drill into the details of the model, and see what the change of water level and the rate of change means, the wave, and what is the forces acting on from the upstream ice pushing to the leading edge. If we can do all that, and if we look at the thickness change and the melting of the cover with the weather condition and water temperature, I'm not saying we have all that now, but if we think like that, we may be able to come up with some formulation for breakup. Okay, in a very primitive way, if we look at just at the water level change or the rate of water level change, and we found that actually the rate of change is more, the breakup is more related to the rate of change of water level rather than the actual amount of water level change. Okay, but as I said, this is just the very, very beginning of this. We need to look into all these other factors, the force, the cover thickness, the strength, all these things. If we can do that, then we'll be able to come up with ways of modeling it. So, in summary, the criteria for mechanical breakup is what we are really looking for. And I think, make it in a simple way, whether it's bending failure or the compressive failure, whether it's due to the wave or the pushing of the ice mass. Both are there. Okay, I'll stop here for questions.
Thank you. And now time for some questions. Eva.
I'm going to comment on your first point. Bending failure is at root a tensile failure. Compressive, of course, is different.
Yes, yes.
Bending failure does not include anything related to friction.
No,
Compressive, of course,
I
does,
agree.
which is a temperature-dependent property.
Yeah.
So
yeah.
these are two very different properties, if you wish.
Yes.
This will be manifested in different breakup characteristics.
I agree. That's what I think we should be. And the model can do both, should be able to do both, if we know the stress parameters. Okay. And hopefully the fracture people can really help us on that. You don't want to get onto the river ice, but it's not impossible with the instrumentation nowadays. Yeah.
Jukka.
Neither you or earlier this morning, Steve, mentioned anything about thermal cracks.
Some effect is there. I just didn't go into the detail.
Okay.
We can calculate the thickness, and as I showed, we can also calculate the deterioration of the cover, with what Ashton type of approach.
Then another question is that you both showed the same photo of a kind of longitudinal crack in the middle. It very much looks like there was thermal compression or something like that. It's not just, it doesn't look just like bending. It looks
Okay.
like there has been some compression.
That I will leave to mechanics guys to say. But the river ice people, let me put it this way. My work has been, as Steve knows, mostly before breakup. Because for years, I was confused by people working on the breakup. And it seems so nebulous. But I'm glad that John pushed me into giving a talk like this, and I began to be able to comprehend what's going on there.
You want to say something, Steve?
Yeah.
Only thing I'll say is that there was a period when people were saying there's thermal cracks, so we don't have to worry about what causes breakup. We just assume the cracks are there, and so in a way we kind of rebelled against that, So we went too far the other way and just totally ignored thermal cracks.
Other questions, John?
So, if you go back to that P star,
Yes, yes.
so you've got the ice thickness in there, right?
Yeah, the thickness, just make sure I don't confuse you. It's the accumulated thickness, the jam thickness.
Oh, it's not the intact ice thickness.
No. We are talking about ice flows moving. Okay, this actually is in some way similar to the ridging in the sea, I think.
But that's the distinct difference between sea ice dynamics and river ice dynamics, right? Your P star, that is a distinct difference, or am I wrong?
I think shouldn't be different. What I'm trying to say is this P star in the original Hibbler model is not correct. Okay? If your P star is a constant, and you have to calibrate that. If it's a constant, you get the same internal resistance. Doesn't matter where you are, doesn't matter what thickness you have, which is not correct. That's why I showed the Bohrhead simulation, because if you use P star as a constant, you are not going to get this broken band in the tidal bay. Yeah. So what I'm trying to say is the P star term should be what we used from the ice jam studies.
I think there are alternatives, and I think we will hear on Friday morning about the alternatives by
That's
Veronica,
good.
sort of.
Yeah.
So alternative formulation for that.
Yeah.
Any other questions? Hey,
You have a formula for the front, the broken front propagation, and you showed it's less than the wave celerity, shallow water wave celerity.
yeah.
Right? I wonder if Danny Dumont's data can be used to check that.
I think it's different waves we are talking about. This is long wave, shallow water wave, not periodic.
But to the extreme, we take limit. It's the same
Okay,
thing.
you can do that. You can see Haley and I, fortunately, unfortunately, we are in the same field, but not quite the same. Okay, then, in the evening, Haley said, "Hey, can we discuss this?" I said, "No." No time. Well, not really. We argue a lot. Yeah.
but discussion is good always. So.
Yeah.
Other questions? No? Okay, we are ready for lunch. And remember then the activity we had in the afternoon here also. And also the dinner. Thank you.